All right, today we're diving into something that sounds, well, completely impossible. It's a proven mathematical theorem that honestly feels more like a magic trick. We're talking about one of the most reality-bending ideas ever, something that makes you question everything you thought you knew about, well, about stuff and the space it takes up.
Just let that sink in for a second. You take a solid ball, you break it down into a few pieces, and then you put those pieces back together to form two perfect copies of the original ball. I mean, identical in shape and size. No extra material, no tricks. You start with one, you end with two. That, right there, is the mind-blowing statement at the heart of the Banach-Tarski Paradox.
So how is that even possible? How can you double something from absolutely nothing? That's the first thing everyone asks, right? It feels like it breaks every law of physics, every ounce of common sense we have. And that's exactly the mystery we're going to unpack today. So here's how we'll break it down. First, we'll look at this impossible duplication head-on. Then, we'll get into the secret sauce, a controversial rule about infinity. After that, we'll talk about what these pieces really are, what this all means for the real world versus the world of math, and finally, what this whole crazy paradox actually reveals.
All right, first things first, the impossible duplication. Now, it's super important to get one thing straight from the get-go. This isn't some clever riddle or a trick with words.
Nope. This is a real, mathematically proven theorem from way back in 1924. Two guys, Stefan Banach and Alfred Tarski, laid it all out. It's totally 100% logically sound, built on the rules of modern math. And what it does is it completely challenges our most basic idea of what volume even is. Okay, so if it's not a trick, then what in the world is going on? Well, the secret ingredient, the key that unlocks this whole thing, is a single, super powerful, and kind of controversial rule for handling infinity. You can think of it as the ultimate wild card in the deck of mathematics.
It's called the Axiom of Choice. And here's the gist of it. Imagine you have an infinite number of drawers, and each drawer has at least one sock in it. The Axiom of Choice says you're allowed to just take one sock from every single one of those infinite drawers to make a new collection. The crazy part? You don't need a rule for which sock to pick, like always take the red one. You just get to say, I'm taking one from each, and the axiom guarantees that such a collection of choices is possible.
And this is where it gets really powerful. See, without this axiom, if you wanted to make infinite choices, you'd need a clear rule, like always pick the smallest number from each set. But with the axiom, you just get to declare that a choice is possible from every set all at once. You don't have to show how you did it, you just get to say it can be done. It's this purely abstract power that cracks the whole paradox wide open.
Okay, so we have this wild card, the axiom of choice. Now let's see what happens when we use it on our sphere. We're going to talk about the pieces it gets cut into. And I gotta warn you, this is where things go from weird to just completely bizarre. Because these aren't pieces in any normal sense of the word.
Yeah, the theorem talks about cutting the sphere, but that's not what's really happening. We're not taking a saw to it. What's actually going on is we're taking the infinite number of points that make up the sphere and just sorting them. We're putting them into a few very specific buckets. The result isn't solid chunks. It's more like these infinitely complex, ghostly clouds of points.
The technical term for these point clouds is non-measurable sets. And they are so fantastically weird, so scattered and porous, that the whole idea of volume just breaks. It becomes meaningless. Asking, how much volume does this piece have, is literally like asking, what does the number 7 smell like? The question just doesn't apply to these things. So, let's put it all together. Here's the abstract recipe. First, you stop thinking of a sphere as a solid thing and start thinking of it as an infinite collection of points. Step 2. You use the axiom of choice to sort all those points into a few of these weird non-measurable sets. Step 3, you just rotate and shift these intangible clouds of points around. And finally, step 4, you put them back together and bam! They now perfectly form two brand new spheres. No gaps, no overlap, just two perfect copies. Okay, I know what you're thinking right now. This is nuts. Can I do this with my coffee mug? Can I duplicate a bar of gold? And that brings us to maybe the single most important point we're going to make today. The line between pure math and the real world. And here's the big reveal, the twist in the story. The Banach-Tarski Paradox is absolutely 100% true in the abstract world of mathematics, but it's also absolutely 100% impossible in the physical world we live in.
It doesn't violate the laws of physics because, honestly, it's not even playing the same game. And here's why. Think about a real apple. It's made of atoms, right? A finite number of them. It has a real volume you can measure. But a mathematical sphere, that's just an idea. It's a perfect, abstract concept made of an infinite number of points that have no size at all. You can't chop up an atom into one of these weird non-measurable sets, but you can play all sorts of games with an infinite collection of points.
So, if you can't actually use this to get rich duplicating gold, then why do we even care? What's the point? Well, the point is that this paradox tells us something incredibly profound about the limits of our own intuition and the strange new worlds that math allows us to see.
I mean, this is so much more than just a cool party trick. It really shakes things up. It challenges our gut feelings about space and volume. It puts the very foundations of mathematics to the test. And, it's not even a new idea, really. It echoes ancient philosophical problems like Zeno's paradoxes. It even has weird conceptual links to some of the measurement problems in quantum physics.
So in the end, that's really the big takeaway here. The Banach-Tarski Paradox isn't some kind of proof that logic is broken. Not at all. What it is a stunning revelation. It's proof that infinity is just way, way weirder than our brains are built to comprehend. It shows us that there are truths about space and numbers out there that our intuition just can't touch.
So no, you can't use this to duplicate your car, but what it does give us is a peek into this bizarre universe of pure logic, where the rules we're used to don't always apply. It proves that math can see worlds that our intuition is completely blind to, which leaves you with a pretty wild thought, doesn't it? If one sphere can become two, what other secrets are hiding out there in the depths of infinity?